Well, the Turing machine has an infinite shape, so
Yeah. I pretend to be a mathematician.
the previous talk has certainly whetted our interest in learning about the kernel method
Catalytic variables.
and catalytic variables, so I think we're all anxious to be informed.
Okay, so thanks for giving me the opportunity to give the last talk at this workshop. My talk has a certain connection to Tony's, and not just in the fact that I'll talk about the kernel method that he already mentioned before, but rather he will continue his talk in Vienna, whereas this is in some sense a continuation of a talk I gave 2 weeks ago, where I gave some nice results that I'd obtained with the kernel method, but I just glanced over the fact that there was a kernel method used. So now I thought it would be good, because it appeared last week and also a little bit this week, to actually give a, shall we say, pedagogical introduction to the kernel method. Now, I feel like I'm a bit of an imposter, because there's people in the audience who've used the kernel method. There are experts like Mireille Bousquet-Melou, who would be much more qualified to give a talk on this. But I think it's such a beautiful subject and really can be used very well in combinatorial enumeration and also with relevance to statistical mechanics problems, that I am going out on a limb a little bit and will tell you about what this tool actually is. If you do a search on the internet, by the way, I just printed this out, there's a comment by Helmut Prodinger on this from sort of an email repository from 2000. The French have a new toy, the kernel method. Unclear where the name comes from. And then he goes on saying, only that much, I've used that also. And then he goes on and on about this. Helmut Prodinger used to be in Vienna, now he's in South Africa somewhere. Stellenbosch. I refuse to say this because my French pronunciation will be terrible. So you shouldn't really take the title too seriously. It's really just a tool to actually explore the kernel method in a reasonable setting. So I'm going to be counting lattice paths. So there's some overlap with Tony's lecture, but they won't be self-avoiding in general. So it's just going to be random walks with the kernel method. And there's going to be a general question that I'm going to ask, namely, you want to know the number of n-step random walks in the quarter plane. So let me just denote this by n0 squared. With respect to certain restrictions, say starting at the origin and ending at some fixed point. And what's important now is that you want these to take steps in some set omega. So let me just give you some example of what I mean. So some subset of the lattice. I'll give you some examples of what you should think about. So here you've got your quarter plane. You start at the origin, and let's say, so you have some coordinates mx, my. So you have horizontal steps in x and y direction. And your omega is, for example, the set of walks. Well, let me just denote this symbolically. You can go diagonally, say. So one step to the right, one step up. You can go down, and you can go to the left. And then you start, say, at the origin. You go up one, maybe down, up again, left, left, left. And at some point, you might ask how many steps are there that start and end at the origin.
And this need not be self-avoiding.
Need not be self-avoiding at this point. There are self-avoiding versions around of this, but it might get a bit more difficult. So I'm actually not going to talk about this particular set. This is a very famous set. This actually has been studied by Creveras, I believe in the 60s, and has been rehashed various times since then. I'm going to look at slightly simpler models, and my set of walks will be chosen for very pedagogical reasons, because I want to show you certain cases of generating functions that will occur within this kernel method, within these lattice path enumerations, which will go from rational via algebraic to definite to not definite anymore. So you really get a whole big class of different generating functions out of this. And I think that's partially where the appeal lies. So I'll start with, well, what would be one of the easiest two-dimensional models would be this one here, which is really just to set some notation. The second one, I'll go up, right, and then maybe allow going down again so that I actually hit the boundary. Otherwise, it's really much too simple. The third case would be something that can be done certainly in other ways, but it's sort of the simplest, non-trivial way of doing a particular case of the kernel method that I'm going to discuss in a moment. Then one that gets more interesting, which has got these steps. And at last, I'll talk a little bit about a step set where you go up, diagonally, down, and diagonally. So you have a finite step set out of very small steps. They all are really having x and y jumps of plus minus 1. So it shouldn't be too difficult, you would think.
Are you
yes.
using two-dimensional because it's pedagogical, but it can live in any dimension?
You could do it in higher dimensions as well, but it gets more complicated. We'll come to the so-called catalytic variables in a moment as well. And these are sort of systems where we have few catalytic variables and where you can actually do things within 60 minutes. So that's part of the reason. So these are the sets I'm interested in. And I'm looking at, so this is, I would think, point 1 here, walks in the quarter plane. And item 2 would be, well, what you do with these things, you want to write down generating functions. You count. You want to do algebraic combinatorics to define a generating function. And you want to derive some conditions that this generating function satisfies. And this leads naturally to functional equations. So of course you can think also in terms of recurrence equations on the lattice, because if you're at some lattice point here, you know there's only certain ways you can have gotten to this point, and this will give you a set of recurrence equations together with boundary conditions on the boundary, and you can set it up like this. But it's much more advantageous to actually go towards the generating function language right away. So I'm going to now write down a generating function. So I'm going to have n-step self-avoiding walks. And now I really...
Not self-avoiding.
N-step random walks. Sorry, thanks. I'm so used to thinking in self-avoiding walks that this slips out occasionally. I'm sorry about that. So I've got a certain number of n-step random walks, which will end at these coordinates mx, my somewhere here, which could be the origin, but need not be. And I will have a generating function x to the mx, y to the my and t to the n. And in the end of the day, I'm really just interested in counting the number of self-following walks ending at the origin again, or ending anywhere, which here would correspond to setting x and y equal to 0, x and y equal to 1. So that's where the idea of catalytic variable comes from. This also happens in other settings where you actually invent extra variables. Here they have a natural meaning, but in other settings you have to find suitably chosen extra variables that you're actually not really interested in. You really want to set them to 0 or 1 at the end of your calculation. But in order for the kernel method to actually work, it is crucial that you have these extra variables in your generating function.
Is that, I mean, it sounds so trivial, I would
Yes.
say. I mean,
So
is
far,
it
yes.
Like if I want to define, say, the spontaneous magnetization of the Ising model, I could say, well, I need the magnetic field, differentiate the free energy with respect to the field, and then I set the field to 0.
But the difference that introducing that variable makes things harder, rather.
I mean, these are easy variables. No, these will turn out to be easy variables to work with. The moment you have a magnetic field, it's I think a lot harder.
But I mean, I can't believe that this captures the meaning of catalytic variable, or does it?
Well, somehow that you're going to get functional equations which close because you have these extra variables, but wouldn't close on the original model.
So just wait for a moment until I write down the functional equation. So g of x, y, and t satisfies a functional equation. So let's just take these couple of cases. Yeah, for instance, in case 1, I just have, so what could happen? I really get a random walk by either having no walk or attaching a walk to my random walk that I already have. And in this case, I'm going up or to the right. If I go to the right, I get an additional weight of x. If I go up, I get an additional weight of y. And that's and then, thank you very much. Of course, I add an extra step, so there will be a t.
Okay, so here your approach is you take something and add one step.
Yes. So you can set up a recurrence on the lattice and sum it up, and you get this functional equation. But I think this is easy enough to see. So here, I mean, you can solve this immediately for g of x, y, t. Nothing to be done, really. Let's look at case 2. So now, what do I do?
And of course, there are boundary conditions that impose this.
Yeah, but here they are. They don't exist because you're going upward to the right. There are boundary conditions, but they don't appear because you'll never touch or want to cross the boundary. Now, this will be different now in case 2. You go up, you go right, or you go down. So right is x, up is y, down is 1 divided by y. So if you did not have the boundary, this would be it, if you were in the right half plane. But as you have the boundary, you now have to think a little bit and say, well, hang on, I'm overcounting here. I have to actually subtract something again. So what do I subtract? I subtract precisely those walks where I would have gone below the x-axis. So what does it mean? If I actually start with walks that ended at the x-axis, so y is equal to 0, so this is just the coefficient of y to the naught here, then I would have included these up here, but I don't want them. So I just subtract exactly this factor here that comes from precisely those walks that before I attached an additional step would have finished at the x-axis and would have crossed it. So this is minus t times 1 divided by y.
Just this without Kronecker deltas.
Yeah, you get the Kronecker deltas if you do recurrence relations. But the moment you sum over things in the functional equations, these things disappear. This is why this is so nice.
Does the one, I mean, 1 is more or less Kronecker tensor.
This is the Kronecker. No, that's the empty wall.
Well, I was meaning in the last time, so yes.
Yes?
Okay.
So similarly, now we can keep going. So what do we have now? Case 3 was 1 plus, and now this becomes really sort of obvious. X plus 1 on x plus y plus 1 on y, g of x, y, t. And now we weren't allowed, well, the same thing happens again, g of x, y. And there's a little bit of abuse of notation. These generating functions, of course, are all different in these different cases. And I denote them with the same symbol just to avoid overload. And here I'm getting minus 1 and
1 over x, t 1 over
this
x.
happens when you don't have slides, sorry. 1 on x, g of 0, y, t. And this is all you need. Now, what's the next case?
Is there not an over subtraction for those two regions?
No, because if you enter the origin, you don't. This will happen in the last case, case 5. So hang on a bit. Yeah. So you subtract these things individually. So you can do the same thing in this case here. So you get 1 plus t. Now it gets a bit tedious. So you have, let's just take x, y first. Or then you walk to the left, but up. This gives you a factor of y on x, or the other way around. And here you just do the same thing again. And again, so this is minus t y on x, g of 0, y, t minus t, x on y, g of x, 0, t. And then, of course, in the last case, so this looks a bit academic right now because these things all look sort of the same thing. But case 5 is slightly different because what you end up with here is the fact that when you count, so let me write this down first. This is going to be y plus 1 on y, which is up and down, or it's going to be diagonal, so it's xy plus 1 on xy, g of x, y, t. And there's a special case to think about here, which is really why I just wanted to mention this. Namely, now if you subtract, and again, you have to avoid going into the negative y direction, which you do when you have set, when you set yx equal to 0. And you have to avoid going into negative x direction, which happens when you set x equal to 0. But now it happens that you've subtracted configurations twice here, namely precisely those that correspond to being at the origin and walking this way. So you've included them here, you've excluded them there, you've also excluded them there. So now this is where it gets a bit trickier perhaps. So what do? You just simply add them up again. There you go. So this is the set of recurrences.
It's tricky. It's just inclusion, exclusion on the last.
Yes. There's nothing deep so far. So we haven't quite come to the kernel method yet. So now we should really come to the interesting bit, namely the kernel method.
Who coined that term?
Beats me. I wanted to actually ask that some conoscenti in the audience. So
Was it blue?
it could be. I'm not sure. So the kernel method. So the idea is really that all these equations have the structure k of x, y, t times g of x, y, t is going to be something. So you collect all these factors together. And what's left on the other side is some sort of g of 0 yt, g of x 0 t, and maybe a g of naught naught t, or in more complicated cases, other nonsense. And you have to think about what to do with this now. So you write the functional equation like this, and k, which I think the French call n, is called the kernel. The French call it n for a good reason, I think.
So, part of income in the Middle Age. You know, like then.
So the idea is now, really, the idea of the kernel method can be written down very quickly. You want to set the left-hand side equal to 0, and then work with the right-hand side. So you consider pairs of variables x, y, which are now related, not independent anymore, so you work on a submanifold, such that the left-hand side is 0.
For all t?
For all t. And I should also say something at this point. You're really interested in the counting problem, which means you're interested in formal power series. I mean, we just want to count, so right now we're not interested in convergence necessarily. You're just really interested in formal power series in T. And if you do these things, you'll get algebraic functions. You get solutions that will not be formal power series in T. So you have to be a bit careful. You have to have formal power series in T. The coefficients can be Laurent polynomials in x and y. So there you allow negative powers, but you have to avoid very carefully negative powers in T, because they don't correspond to the solutions regular at the origin, so not the solution that correspond to the solution of a counting problem that you're actually after.
Also, x and y are only positive powers. You can only go up starting from the origin.
Yes, but you will actually get intermediate solutions where you actually have to allow negative powers.
This equation, x
Yeah?
and y will be related.
And yes, you get a relation. Don't forget. And don't forget the right-hand side encodes the boundary conditions. If I just look at the left-hand side, this is like the free problem, so to speak, no boundary conditions. And I can walk to the left and walk down arbitrarily at that point. Yes.
But see, k is 1 plus t polynomial in x and y, isn't it?
No, just,
Plus t squared plus.
no, it's not 1 plus.
K is the inverted one, 1 over 1 plus t.
Yes, yes.
No, 1 minus,
So yes, so if you have just the counting problem, look at case 1 here, right? So anyway, so consider this one here. Let me just finish what I wanted to write and work with the right-hand side. Yeah, if you got the right-hand side, you can, so formally, it should be sort of obvious. Here you have a functional equation, 2 variables, x and y, in the catalytic variables. T is sort of very silent as far as the functional equation is concerned. Yeah? You can think of trying to iterate these things as well and do various other things. What you want to do now is you really want to reduce the number of variables. So if you set the kernel equal to 0, you get y as a function of x. So then the right-hand side will give you, in general, a more complicated functional equation, but just in one variable, because the y is really now a function of x.
And sorry, I have to interrupt you again, but if I see this equation, the kernel really has the form 1 minus t
Yes.
a Laurent polynomial in something.
Yes.
So it cannot
Yes.
be identically 0 in t, because for t equals 0 is 1. You
No,
want that.
it's not 0 in t.
Okay, so the
T is a
relation
variable.
between
T
x
is a
and y.
variable now.
So the
But
relation
x and y depend on t, or you choose them
No,
without.
x and y depend on t. Yeah.
I thought that you
Again,
wanted
example.
k is identically 0 in t for fixed
No,
x and y.
No.
No,
So really consider pairs of x and y, and t is still sort of, so y will now say become a function of x, which also still depends on t. T is a silent variable. You're supposed to forget about t and just pull it out of the hat occasionally.
It will all become clear with an example.
Yes.
Exactly,
So-
exactly, you're right.
Yeah, so case 1 is very easy. You just have, I shouldn't even write this down. What do you get? G of x, y, t is equal to 1. So I shouldn't call this a kernel method because you don't set the kernel equal to 0. You just divide through. So you do g of x, y, t is equal to 1 on 1 minus t x plus y. And maybe just so I can name something after myself or after somebody, let's call this the obsolete kernel method. Because there's really not a kernel method here at all. This name will become clear later on because there will be something like the classical kernel method, the obstinate kernel method, and the iterative kernel method. So this is the obsolete one to start with. Oh yes. So, and of course, here the generating function is rational. So this is very easy. Now you can expand and get your counting coefficients if you want to. So case 2 will be a bit more complicated. One minus t, 1 on y. I've got it written down here somewhere, but I just want to sort of write it down in the kernel here as well. So you've got k of x, y. You could have multiplied through by y. You see this is linear in x, quadratic in y. Now if you want to set the kernel equal to 0, you sort of see that you can write this kernel in a suggestive way. I mean, it's quadratic, so you can factorize it. And you get 2 roots y1 and y2, which now are functions of x and also functions of t. Yeah?
Okay, so one could also think that you would solve this with respect to x, but I think
Yes.
you do it with respect to y because the y is not sitting in the g on the right.
I'm sorry, you said
Exactly, that's the point here. I want g of x, so I could solve it the other way around, but that would give me a complicated equation now where I have an x of y inside the generating function. So what I'm after,
I'm sorry, are you saying that this is the kernel or this?
Yes, this is the
that is the kernel. So this factor k is the kernel. And the whole game is set the kernel equal to 0, work on a submanifold, and see what you can do. So at this point, you can also, if you want to solve y1 and y2 explicitly, maybe the one thing you should consider is, I don't think I want to write these things down necessarily. You get 2 roots y1 and y2, which you can solve easily. And what's important to note is that y1 as a power series in t starts with t, 1 times t plus higher order terms. Whereas you've got y1, y2 is equal to 1, or in other words, y2 starts as 1 over t plus higher order terms. So if you want to solve this as a counting problem, the idea is now the right-hand side equals 0 should now be an equation for g. And you see if you plug this in correctly, you see that g is equal to y divided by t. And if you substitute y2 for y, you see something that cannot solve the counting problem. So this gives you an indication of which solution to actually substitute. And so what you do here is now at this point, so you set g of x naught t is now just equal to, and you substitute this 1 on t times y1. So you have to pick the right y1 cancels the t, starts with 1 plus, which is really the solution to the counting problem. So you choose this route, and this already solves for you now the counting problems for walks ending on the x-axis. You're done. And then you have this, and you can substitute this. And there's a small other miracle occurring here. Because if you just formally substitute 1 minus t, let me just write this down, divided by the kernel. And what you do now is you make x and y independent again of each other. So you just use the y1 to solve this one here. But the factorization of the kernel, of course, still is valid. So if you plug this in here, and there's a factor missing, I believe, 1 minus t1 on y, jumping ahead while writing, you see that this actually simplifies to 1 on t times y2 minus y, where now y2 is the other root and is a function of x, interpreted as a power series in t. And you get the solution, and from this you can work out what the counting coefficients are, if you want to. Again, I don't have time to do those things. I just want to say these things very quickly. So this is what I would call the classical kernel method. And this one here has been done with more or less the same setup for dict paths or something related to dict paths, I guess, by Knuth in The Art of Computer Programming. So as far as I'm concerned, this really goes back to Knuth. And the other thing you notice here, y2 is now the solution of an quadratic equation. So now we are in the realm of algebraic generating functions. So I hope this isn't too simple for.
Is it always an ambiguous to understand which root is the good one, or you have to take a few?
Well, you basically look at these things. For higher power, for higher degree kernels, you also get Puiseux expansions and fractional powers of t, and you just hope, and somehow it always works out. I don't have a proof for this, that there's sort of one good solution.
Well, in principle, you can calculate by hand the first few,
Exactly.
few
Yes.
points in G.
Yes. And you basically compare to I mean, you can do the counting problem, and you compare, and then you see what you have to do. So it now becomes a bit more interesting if you actually look at the third case, which, of course, I should say, little disclaimer, this can be done so much more easily without the kernel method. So please, all the combinatorialists here, excuse me for doing it with the kernel method. This is really just to prove the point. I mean, what do you do? Part 3 was, and I erased this unfortunately, part 3 was essentially these walks here. And you see you have independent steps in the y direction and x direction. So you can solve the problem for x and y separately, then shuffle these steps together, do some counting, you get an answer to the counting problem pretty much immediately. So I don't want to do that. This is really a pedagogical way of looking at something that happens within the kernel method now. So the nice thing here is, and let me just write this again, 1 minus tx plus 1 on x plus y plus 1 on y times g of x, y, t is equal to 1 minus t, 1 on y, g of x, y, t, minus t, 1 on x, g of x, 0 t, g of 0 y, t. So at this point, you have to look for some extra ingredients, extra information that you can see. So one thing that helps you and that makes these problems feasible in a short time is that you see immediately that the kernel has got symmetries. Yeah? Which symmetries are these? First of all, x and y can be exchanged, which also transfers to the generating function itself, which you see clearly from the picture here. But also x to 1 on x symmetry in the kernel, and y to 1 on y symmetry. And we had this 1 to 1 on y symmetry over here already as well, as you see. So this makes life a little bit easier. So what do you see now? And this is where it gets a bit trickier, perhaps. So first of all, if you solve this, it doesn't really matter if you solve y as a function of x or s as a function of y. So let me just do this again. If I set this equal to 0, I'm getting one function, just as over there, which is now dependent on, first of all, it still depends on t. I'll suppress this. I'm really only interested in depends on x. And you see x plus 1 on x appears jointly here. So this is really a function of x plus 1 on x, which also, if you want to, still depends on my t. And if I look at this as a formal expansion, I pick now the root that, just as over there, grows like t plus higher order powers. So if I write like this, it should really be equal to t plus higher order powers. And because of the symmetry, y1 times y2 is still equal to 1, and y2 again goes like 1 divided by t. So I sort of know the good solution. And now, if I look at the right-hand side, I see I have now two functional equations. OK, I can still use the symmetry to write this as g of y naught t. So this is really the same function, once with x plugged in, once with y plugged in. But I've got my y of x inside the generating function. So the idea is now to really try to iterate. You have the right-hand side equal to 0, which gives you a functional equation. And the idea is now to iterate in order to solve this. And I'm not going to do this in detail now. You just have to believe me. If I start with x and iterate, I'm getting either y1 or y2 from the kernel. I pick the y1. Now I plug the y1 back in and want to get another x for this. And again, I have two solutions for this. One actually will get me right back. The other one will, in fact, in this case, because of the symmetries, get me to 1 divided by x. If I continue, I'm getting 1 divided by y1, which was equal to y2. And I'm getting a cyclic group here.
When you say those arrows, you mean at the first step you solve for y in terms of x.
Then I
The second
solve
step,
for
you solve
x in terms of y,
y.
and so forth. Because of the symmetries here, it's more or less the same thing. So I don't even have to distinguish if I don't want to. But I'm getting a finite.
Whatever solution you have, this is substituted in the equation to get you system of equations for the gx0.
Right.
0y.
So now I have to be a bit careful, because even though I can formally iterate here, if I now substitute these pairs that I have into the right-hand side, so I really have pairs of solutions x, y1. Then I've got 1 on x, y1. Then I've got 1 on x, y2. And I've got 1 on x, 1 on
X 1 over 2.
x,
1 over y2.
x, y2, yes.
Y2.
So now, if I work with these variables, and the right-hand side should solve the counting problem, a little bit of inspection and just formal expansion will show you that y2 is not admissible here. So these pairs I actually cannot use. This is where it gets a bit tricky, and
Because
where
you would get a whole series in t.
you get negative powers in t, which you don't want. And only one negative power in t is enough to kill your method at this point. There's a slightly different version of the kernel method that still can deal with something like that, but it's more involved, and I want to touch upon this here. So you plug these two pairs in, and what do you get? You get, if you look at the right-hand side now, you get xy1 if I multiply through, is equal to tx, g of x naught t, minus ty1, g of naught y1 t, and I'm getting 1 on x y1 is equal to t times 1 on x g of x naught, sorry, g of 1 on x. So this looks now nasty because you've got these negative powers here that you don't want, right? So you get two equations. You take the difference, and you get something of the type tx g of x naught t minus t1 on x g of 1 on x naught t is equal to x minus 1 on x times y1. So let me just put a little box around here, because this is really the equation you need. Now it needs a bit of thought to actually understand what's happening here, because this is slightly intricate at this point. Let's hide all the other bits. Just focus on this equation here. We've got these negative powers here, which we don't want. So somehow we have to get rid of these things. But if you look at these things, these are counting functions. These are power series in t. This counting function will have only positive powers in x, right? Whereas this one here will only have negative powers in x. And the right-hand side, remember y1 is a function of x plus 1 on x. Will, as a power series in t, have positive and negative powers in x. But now you see, all you need to do, this is what we're after, is to actually extract what's called the positive part of the right-hand side. Yeah? So you extract the positive part here and run with that. So,
but up to now, in this problem, sooner or later, you have to admit that it's separable in x and y.
It's what?
So
It's simpler in x and y.
Yeah, so you have to admit that sooner or later, I guess, using any kind of solution. So this is the point where you admit it now. But is that a general feature?
Separable.
Oh, separable.
Or separable?
Yes.
No, unfortunately not. So there are.
So the step that you are taking now, that's just admitting that fact for this particular
For this
problem.
particular problem, which enables me to do this in this 1 hour lecture or 1 hour talk here. Okay? So, but the general feature appears in other systems, other models you can do as well. That you have to look out for things like this to happen, which then allow you to actually proceed further. I mean, if you just are interested in the Tony Goodman style of iterating functional equations without solving them, you can do this very generally. These functional equations, once you set them up, allow you to iterate. But if you're interested in closed form solutions, you need extra structure like this to do something. Okay? So you want to extract the positive part. So you can write y1 now as, and now let's put the t back where it belongs. So you've got a doubly infinite series. AL of t are now nice power series in t.
May I interrupt you
Times?
for 1 second?
Yeah.
Is it true that you can understand the derivative in x equal 1 easily? The derivative of g at x equal 1. Because that would simplify many things. There will be an epsilon over epsilon, which is 1. Say
you want to take the limit of x to 1 here.
x to 1, the limit is
and then use L'Hopital or something like that.
Yes.
Yes. You can try playing around with this and you actually get some way here. You get a differential equation in G, which you can then solve. Yes, you can do it for this here.
But there's no good.
But G prime at only x equals 1 isn't going to help you solve the original problem.
Yeah.
No. So, I mean, you can try something like this, but it's sort of, sometimes it works, sometimes it throws out too much. So you really need to work with these things. And then I actually just developed this particular thing at the beginning of the week because I was hunting for a very simple problem. I was talking to Olivier Bernardi. He said he's done precisely this one a couple of years ago, not published, because it had to do with enumeration of maps of some sort, right?
Yes, it has to do, this works in bijection with three-rooted maps. So if you want to look at this work differently, you can. And I was just interested in solving the equations, like you are doing.
Yes. So at this point, I'm now shamelessly using a result from you, which basically says you can get this result by Lagrange inversion. So you can actually get AL of t as a nice sum. I just want to be a bit more definite here. So let me just write down what you get to give you a rough flavor of the sort of complications that you still have to play with. 2k plus absolute value of L plus 2, choose k plus absolute value of L, and then you get 2k plus L plus 1, choose k here. So you get things like this through inverting the kernel equation formally as a power series in T. I mean, this is a classical method. There's nothing new here. So,
but do you need, isn't y1, didn't you say it starts at 1 over t and then it's positive
no,
power?
y2 is the one that starts with negative power.
Y1 starts with what?
T.
With t.
With t. Sorry,
y1 starts with
but
t.
I mean, I'm sorry, as a function of x, that's what I meant. As a function of x,
It has positive.
There are no negative powers.
oh, it's positive and negative.
Sorry. Yes.
Positive
so
and
here you've got negative and positive powers here.
Sorry.
Yeah. But so
And it's symmetric for x going to 1 over x as it should.
yes.
Oh, I see. So there's not an easy way of just extracting the positive part without actually explicitly.
No. I mean, you can formally write down the Cauchy formula if you want to.
Yeah,
The Cauchy
1 over
integral.
1 minus that. Well,
You can formally write it down as a contour integral, but it doesn't really. If you want to do asymptotics, it's okay. But if you want to do more intricate counting, you can't go around Lagrange inversion, I believe. So g of x naught and t is now just simply the sum L from naught to infinity. Now you take this information here that there's a 1 minus 1 on x here. You shift the exponents a little bit, make sure the things you don't want to become 0. You get a sub L of t minus a sub L plus 2 of t divided by t times x to the L. So this cancels such that there's no negative power of t here. You see this perhaps most easily by seeing that there's a t to the power plus 1 always here. So you really get something well defined. And you can plug it all in and now solve for g of x by t just by dividing through the kernel and plugging g of x naught t and g of y naught t into the numerator.
The result will be written in terms of these AL of t's.
Yes, and you can. I mean, you know, if you now feel like a masochist, you can push this and get more information if you want to. But in principle, this is now solvable. So this is one example of the so-called obstinate kernel method. I think obstinate because it's actually harder to actually do something at the right-hand side. So just setting the kernel to 0 is not quite enough anymore. And it very much rests on the fact that you have a finite Galois group here. So that under iteration you actually get some sort of cyclicity or something like that. So that's when these sort of methods come in handy. This, I think, was championed by Mireille Bosquet-Melou. Other people who've worked with this are Andrew Regnitzer, myself, Max van Rensburg, and there's a very nice paper by Marnie Mishna where she's actually done lots of the walks in the quarter plane problem and tried to classify them in some sense.
It always happens that within this framework, G is always some hypergeometric one.
No, we'll come to this next. In the remaining, we started late, 10 minutes. So this is, now I should say this, thank you for mentioning this. This is still differentiably finite. So in the sense that you have some sort of...
Not algebraic anymore?
I don't think this one is. Even for the...
But you're going to get the solution as these infinite series.
Yes, but
then
they
you'll eventually
allow
be able-
polynomial recursions.
But then you will find.
Yes.
Yeah.
So if you look hard enough, you find these things. But again, this is not part of what I want to talk about. This method also applies to the so-called Crèverat walks that I started off at the beginning.
No, this must be still algebraic because this is just products of payload paths.
Yes,
okay,
but
yeah,
but
there's a shuffling, there's
if you do the shuffling, you get exponential counting in there. So it's not. I don't think so.
Okay.
No. Please convince me otherwise afterwards. And this also applies to the Crèverat walks. And there, despite having a more complicated obstinate kernel method, you've got a cycle of length 6 now. You get a algebraic generating function. In fact, it's cubic. So you can still do slightly more advanced things there. So now I actually want to come to the things that are most closely related to my own work, namely the case of the, what I would call now the iterative kernel method, which in my view is sort of, well, it's not necessarily worse than obstinate, but it needs some other techniques and some more miracles to happen to do something. I mean, if you've got a finite cycle, you still have a finite problem. The moment you have to start iterating without closure, it gets slightly harder. So this is the case 4, which is 1 minus t x divided by 1 plus y divided x by y plus y divided by x plus xy g of x, y, t minus t x divided by y g of x naught t minus t y divided by x g of naught y t. Again, you have got xy symmetries.
Sign missing in that one, is it close?
Oh, sorry, this is equals 1 minus. Thanks. So, and to just give you the picture of this again, now you have random walks that can go these ways. And if you start at the origin, you see that trivially you can never return to the origin anymore. And you have something, if you turn this slightly like a random walk in a wedge if you want to as well, directed random walk in a wedge. So we're now getting closer to things that I actually have looked at myself. So now here in this case, k of xy equals 0, let me just very briefly indicate what happens and why it still works. The kernel equal to 0 leads to an equation. Now I'm writing this purposefully in 1 divided by y in inverse powers, because I want to point out that you've got a quadratic equation now. Well, yes, you also have a quadratic equation in y, but if you write the quadratic equation in 1 on y, this took us quite a while to figure out a related problem. We saw miracles and we didn't understand them until we did this simple little trick. Now if you think of solving y in terms of x, you see that the two roots, 1 on y1 plus 1 on y2, actually are equal to 1 on tx. So the sum of these roots is, yeah, so what does this tell you? If you now iterate, you see you actually have a 3-term recurrence here, a linear 3-term recurrence. So in fact, you can formally solve this by iteration. We've done this further on the computer, gotten lots of surprisingly simple-looking formulae, until we finally realized that even though you iterate by substituting square roots into square roots into square roots and so forth, if you write it slightly smarter, you see that there's actually a nice pattern hiding behind. So you get iteration by a 3-term recurrence. Yeah, so this can be solved by an exponential ansatz. And you also see immediately you don't get a cyclic structure anymore. You just keep iterating. And in fact, it turns out, when I call xn the nth iterate, so I still get two roots y1 and y2. I pick y1 as the nice root and take the compositional power, nth power of this, apply this to x. I get that this actually grows like xt to the n. So with every iteration, forward iteration, actually pick up additional powers of t. So I can never close. Yeah? But you can still formally iterate this. And you get a very lovely formula here. Kind of miffed that I didn't do this myself. This was Andrew Regnitzer and Marnie Mission on a wonderful paper that I highly recommend to read. Actually, I don't think you can read it yet. It's not. There's a previous version on the archive, which I don't recommend you read. Wait for the other one. And so you iterate the right-hand side. And because we're running short in time, let me just tell you that now g of x naught t is equal to 1 on x squared t times the sum, and you can just verify this by substituting back into some alternating sum times products of this iteration. You see, if you multiply it through, you get something like x times y is equal to the sum of these g's. You iterate by substitution, and you get this formula, which then you can substitute back into the original counting problem, and you get g of x, y, t out of this. The interesting thing now is 1 on xn really looks like some sort of a lambda to the n plus b lambda to the minus n, where lambdas are Catalan generating functions. So you get higher powers of Catalan generating functions. Actually, you want them now in the denominator. And if you look at the accumulation of singularities, you get very strong hints that this is actually definitely not differentially finite anymore, which this hint can actually be turned into a proof with quite a lot of hard work. And so you've definitely left the realm of nice generating functions, so to speak. And so I should just say that this is called the iterative kernel method, or I would like to call it the iterative kernel method, which to some extent we started developing looking at the model that I was talking about 2 weeks ago in the previous workshop. So I just want to mention this very quickly, and maybe just as a little thing at the end, this is such a cute result. Of course, you can do asymptotics now again, and to just say if you now really do what you want to do at the end, you want to forget about x and y. I'm only interested in walks that actually ending at the origin is useless here, because that number is 0. So I want to count walks that end anywhere, n-step walks that end anywhere in this quarter plane with this step set. And I'm just calling this CNT to the n. Getting an explicit formula is useless, or rather hopeless, I should say. But what you can do at this point is you can do actually asymptotics, and you get a very nice formula. There's some coefficient alpha here times 3 to the n. 3 to the n, you sort of understand if you're not near the boundary, you have 3 ways of continuing. Everything else is mediated by the boundary, especially the amplitude. You can get the correction term.
There's no polynomial correction.
There's no polynomial correction because the boundary actually, in some sense, you get away from the boundary here. So it's possibly a bit surprising, but I mean, you basically have a directed model. So, and for directed models, you have linear growth in the diagonal here, and the perpendicular growth is like root n, so the walks don't see the boundary asymptotically. So it only appears here. So in some sense, physically, there isn't maybe that much of interest here because all the exponents and the growth you can more or less kill off by sort of rule of thumb arguments. But what you can still say here, and this is where it actually becomes really cute. Let me just finish off with this. This alpha, you can compute exactly. It's equal to 1 minus 2 times the sum. And now you get a very nice formula, an alternating sum involving inverse quotients of products of even Fibonacci numbers. So just to have some sort of nice, beautiful result at the end, I think I want to close with this, except for saying I pointed out that there was a model 4, a model 5 around. That model is actually unsolved as of today. Lots of people tried very hard, and this model 5 is the model of Gessel walks. So Ira Gessel found and conjectured a very nice formula for walks returning to the origin. I don't want to write this down, but it's in what people here, I think, call nice formulae, except some people take objection to nice, perhaps. So a nice product formula. So what is this model? It's essentially a model where you go up or down or along the diagonal, again with boundary conditions in the quarter plane, starting and returning to the origin, or starting and returning to anywhere. This cannot be done so far. You can write down the function equation. I've done it for you. But for some strange reason, you cannot solve it yet, even though people tried very hard. And this is, let me just say that these are Gessel walks. And this is an open problem. And in a recent paper by Doron Zeilberger and the co-author, whose name I unfortunately forgot, he calls this the holy grail for lattice path counters. Now, other people might disagree that this is the current holy grail for lattice path counters, but I just want to quote this to maybe get people interested in looking a bit deeper into these things. So thank you very much for listening.
This generate more questions.
Well, in fact, I realized that in quantum gravity and random lattice models, we have been using this method without knowing it was called the kernel method for many years. And for instance, this kind of iterative case, it has been met in many models. So the case where you don't come back to the same value.
Yeah.
And in fact, most often it has a solution in terms of theta functions. And here
yes.
I can read, well, what you call the kernel is what we used to call the spectral curve. And here, indeed, it is a square root of a fourth polynomial of x. So it's a torus. Mm-hmm. And on the torus, you can probably find a solution with theta functions. I mean, it looks very much like the equation for the Potts model
yes.
or the ON model.
Yes, well, I mean, here you don't have a theta function, but the model I was talking about at the last workshop, we actually get a theta function. I mean, you substitute it with other arguments, so but you get theta function type structures for some of these functional equations, for some of these models, yes. And as far as I know, this is also being used by statisticians who call it something else again, who don't call it editing, who just do it. So it's by no means a new method, but at least in this community, it's sort of appeared recently and presumably been reinvented many times, and it's a very useful tool which deserves to be more widely known. So,
in quantum gravity, this was used 20 years ago.
Sure. Could you send me some references, please? I'd like to hear about this. Things a bit more.
Well, in fact, in quantum gravity, that's in random matrices, that's what people call the loop equation method.
Okay.
When you have a loop equation method, usually you have only one catalytic variable, and everything is very simple.
Louder, please. Louder. We don't hear.
In usual equation of this type, you have only one catalytic variable, and yes, there are methods like quadratic methods and everything, and you can solve it. But here it's more complicated. And I don't know
but
where
it looks very similar.
Yes.
Well, this is turning technical. Yeah. Oh, there was actually.
No, I just wanted to say. I mean, it's a similar thing. It also appeared in some other physics literature where it's actually called the. Some of the things are called pole cancelling mechanism because you cancel the poles from from both sides of the current method. Basically.
Yes.
So there are also some results are quite known, well known actually.
Yes. So the pole cancelling, that's the classical method.
That's more like the classical method.
So these new developments, I think, are hopefully new, or maybe have been invented elsewhere already as well.
No, I mean, those problems were not studied, but maybe there is a bijection which
You insist on.
I just would like to make a comment. The fact that the kernel method so far failed for these Gessel walks, although it's known that the number when you go from the origin back to the origin is a very nice product formula. The reason may be that generating functions is not the right tool. Generating functions cannot do everything. And for example, the things that I showed in my talk, with plane partitions and so on, for many of the formulas, generating functions have nothing to say. You have to use other methods.
Yes.
So it may be that the generate functions are not the right method. Maybe they are still, but it may also be that the generating function is not the right method and you have to find some other approach.
But one has to see the coefficients for going somewhere else are nice or are bad. If they are bad, you cannot sum the function as a function. If they are nice, you can.
Yes.
So maybe having a look at the numerical data for the nearby lattice points is a hint towards this, isn't it?
Well, yes, people have tried this, and I think there's only a nice product formula if you return to the origin in this model.
Yeah, but I would imagine if you go just one step away, then it's
polynomial
nice
in front,
each
It's
time,
some,
a
and
little
then you-
polynomial and things like that.
But the more you go far, the more the polynomial becomes ugly.
Exactly.
So
Now
that's
you
why
have
I
to
didn't
control this.
understand it.
Yeah, now you have to control the polynomial. It may still be possible.
So, I mean, what I want to say with
The
this...
last word. I mean, you can speak, but not.
No, what I just wanted to say with this example is really to hint at the fact that there are still unexplored avenues, that the kernel method can do quite a lot. It may or may not be able to deal with this particular problem, but it really serves as a nice method when it works to actually derive generating functions. So.
Well, thank you.